But what is gamma average? Well, gamma is tau over g, or tau is equal to g times gamma. And tau, in the most direct sense for a cantilever like this, is just the V divided by the area that it's acting on, the cross-sectional area of that beam. So we have V of S is approximately V over A, the whole thing divided by G, times L. And this, of course, does not capture this well-known shape factor. So what we're going to do is try to say, well, what does tau really look like on this profile? What's the distribution of tau here? And of course, you know that it's a parabola. So let's take a look at that variation. And then we could apply this conservation of energy, again, with slowly applying loads here. So we have 1/2 the load, Vy, and the displacement that we're targeting, Vs, is equal to 1/2 the integral of tau squared over G d y here. That's a y. So U is G gamma x squared over 2, 1/2 G x y gamma x y squared. So we have, and the issue here is it's a little subtle. Typically, I derive this for force and displacement, but now I'm talking about stresses and strains. So there's a little bit of play in here. You could read up on that if you'd like. So for a cross-sectional area with B height h, we know that the parabola distribution looks like this. We know what it is at the peak. I hope you remember this handy-dandy formula, 1.5 V over A for a rectangle only. That only applies to a rectangle. And then if we're clever, which I'm not, but maybe some of you are, you could derive the parabolic function based on 3 points, 0.10, 0.2, 1/2 V over A, 0.30. So I just found it. It makes sense here that at y equals 0, we get 3/2 V over A. And at the extremes, we get 0. So this is the parabolic distribution for tau. Pop that into this equation. We're integrating from minus h over 2 to h over 2, because y always emanates from the neutral axis, which I think I showed you here. Yes, I did. So it emanates from the neutral axis, so that's why our limits are this way. And you could integrate this, and you get 1.2 VL over GA. And this is the famous 1.2. I'm sure you've seen this before for rectangular shapes. For other shapes, that number is different. So you can find K values in your book for wide flanges and things like that, okay? So in general, the strain energy for a beam is a combination of bending and shear. But typically the energy of the bending is much, much larger than the energy for the shear. In other words, it's much less efficient in bending. It's an inefficient way of carrying load. So I'll tell you when to turn on the shear deformation or when not to, okay? So let's look at an example that, again, is embarrassingly simple but rich in mathematical ideas. And that's a cantilever beam subjected to a point load. X is starting from the left here on this example. And we will start with equation 6.3-6, which we just looked at previously. U bending only is 1/2 integral of m squared over EI dx.